Okay, let's get started. So, as I recall, I left off. Actually, let me download the assignment number 8. As I recall, we started with the first question. Yes, sir.
Copy of the homework 8.
I did not bring any copy with me, unfortunately. Okay, so this is assignment number 8. And if I remember correctly, I did number 1 and number 6. So my question to you, have you tried the others? And if so, any difficulty or challenges in doing these problems? Basically, in order for you to answer the questions here, you need to follow this diagram here, which helps you to establish the configurations of oh, let me turn on the projector. Right, so that diagram is what we need in order to correctly write down the order of the subshells so that we can have the correct electron configuration of the particular atom, all right? So what I'm going to do is continue our discussion of electron configurations and the consequences of that in terms of where different elements will end up in the periodic table. So this here is basically very simple representation of the periodic table as to the different regions in the periodic table that have special names according to the type of electron configuration of the different atoms in those regions. So the regions that are colored blue, right? The elements that occupy those regions, they are called main group elements, right? So we're talking about groups 1A through 8A, all right? And then the second broad category is what we call transition elements, which occupy collectively this region right here, and also this region right here. And in fact, the region here, these are called transition elements, and this region here, the elements in that region are called inner transition elements, right? Now, the main group elements, what you'll find is that as you go from one element to the next across the period, an electron will be added to either an s orbital or a p orbital. On the other hand, when it comes to the transition elements, basically what will happen is that electrons will be added to an inner shell, usually a d orbital when it comes to the transition elements here, and an f orbital when it comes to the inner transition elements. So that is what is being shown here in this diagram, right? So the elements in the main group region, as I said before, electrons are added to an s orbital or p orbital. And more specifically, if you have electrons being added to an s orbital as you go from one element to the next, then those elements are said to belong to the s block elements, which are basically elements in groups 1A and 2A, right? Over here, where you have electrons being added to p orbitals of the valence shell, then the region here is, well, the elements in that region of the periodic table, they are said to be p block elements. And then in this region here, where as you go from one atom to the next, an electron is added to a d orbital, then we say that this is a d block region. And then here, where electrons are being added to an f orbital, we say that these elements are f block elements, all right? So those are just some of the broad categories of elements in the periodic table based on their similarities in their electron configuration. Okay, So, and this is just highlighting one example, elements in group 4A, right? They have 4 electrons on their outer shell. 2 electrons would be in the s orbital of the valence shell, and then 2 electrons would be in the p orbital of the valence shell, and that is demonstrated by silicon here. Silicon has a valence shell where n is equal to 3, so therefore the configuration of that shell would be represented by this right here, 3s2, 3p2, all right? And then if you look at the element below silicon, which is germanium, its outer shell configuration will be 4s2, 4p2, and so on and so forth, all right? Okay, and then this is another example here for rhodium. Its electronic configuration ends with 5s2, 4d7. Okay, so this question is asking, an example here is asking for the ground state electron configuration of the strontium atom, I'm sorry. So strontium belongs to group 2, and what's the atomic number of strontium? I can't see it from here.
38.
38, okay. So the atomic number of strontium is 38. So what I'm going to do is go back to the diagram I showed you earlier, which helps us to establish the electron configuration, the order of the orbitals, right? So basically, let me just write it down here. Strontium has an atomic number of 38, which means it has 8 electrons, right? So following this graph right here, this diagram right here, the first 2 electrons will go into the 1s orbital, then 2s2, then 2p6, then 3s2, then 3p6, then the next will be 4s2. All right, so that's 20 so far. And then after 4s2, you have 3d 10, so that's 30. And then after 3d10, you have 4p6, so that's 36, and then 5s2. So just to make sure, up here is 20, 30, 36, 30. All right, so that would be the electron configuration of strontium. So I think that's one of the questions that was asked. Okay, so we have answered the A part, which is the electron configuration according to the SPDF notation. And then this is asking for the noble gas core abbreviation. So basically, if you remember what we said, to get the noble gas abbreviation, we look at the periodic table and we look for the element in group A that comes before strontium. And that would be what? Can't see it from here. That would be krypton, right? Right, so krypton has an atomic number of what?
46.
36, right? So what that means is that all of this here, it would be representing the electron configuration of krypton. So we just put Kr in parentheses, and then we write down what is remaining after that, which is 5s2, and that would be it. That would be the abbreviated electron configuration of strontium. All right? Okay, any question about this? Any questions? Any questions? So based on that, what we just did, the second half of that first question involves basically doing that. Now, let me clear this and scroll down to see what's next. Okay, so what we're going to look at is how do we apply the Aufbau principle to elements beyond potassium, right? So we're going to start with scandium here, right? Now, let me just say that there's one arrow that is present in this diagram here, right? And it is that the 4s subshell occurs in terms of the energy order. The 4s subshell comes before the 3d, right? So in actual fact, this should be flipped, right? 4s before 3d. And the same is true here, 4s before 3d, all right? So that's an arrow in how this is presented, all right? So keep that in mind while we're going through this exercise right here, all right? So, basically, we're going to start with Scandium. Now, this part here, of course, represents the electronic configuration part, which has the same arrangement as argon, right? So what we're looking at now is what happens when you start adding electrons to scandium to get to the next element, to get to the next element, and so on. Now, of course, what will happen is to get from scandium to titanium, you're going to add one electron to any one of these orbitals. And that's what is shown here. And remember, when you're adding electrons singly to a set of degenerate orbitals, the electrons must be spinning in the same direction, right? And that's for the ground state configuration. So that's what's done here. And then to get from titanium to vanadium, you add an electron here, spinning in the same direction. And then something kind of unusual happens, which you probably would not expect, right? Based on what we have learned before, right? Because you'd expect that to get from titanium to vanadium, all you have to do is, to get from vanadium to chromium, that's what I meant to say. To get from vanadium to chromium, you just add an electron here, right? In other words, you add an electron here, and that would be the electronic configuration of chromium. But it turns out not only an electron is added here, but one of these two electrons is taken from here and added to the next vacant orbitals. So you're going to end up with the 5d subshell being half filled, right? And the reason for that is that it was found out experimentally that this is the most stable arrangement where the 5d subshell is half filled as opposed to being filled up to the fourth subshell by a single electron, all right? So as stated here, the half-filled D subshell plus a half-filled S subshell has a slightly lower energy than what you'd expect for S2 and B4, all right? So that's the reason why that happens. So therefore, the actual electron configuration of chromium in the ground state is what you see here. Okay, so to go from chromium to manganese, we have to add an electron to the 4s sublevel, which of course is the lower sublevel in terms of energy. So we end up with this here. And then to get from manganese to iron, we add an electron here, which is spinning in the opposite direction. And then to get from iron to cobalt, we add an electron here to get that electron configuration. And then to get from cobalt to nickel, we add an electron here, and we end up with this right here. And then another unusual thing happens as you go from nickel to copper. What happens is that an electron is added here. So you'd expect that to take place, again, based on the trend. But not only that, an electron from the 4s sublevel will end up over here. And therefore, you're going to end up with a completely filled 3D sublevel, all right? Again, experiment shows that the filled 3D sublevel plus a half-filled 4s sublevel is more stable than what you'd expect for S2 D9, 4s2 3D9, all right? So that's basically something, as I said before, that based on the trend, you would not expect that, but it turns out that experimentally, that's what you end up with. And then finally, to go from copper to zinc, all we have to do is add an electron right here, and you end up with this electron configuration, right? So that's basically what happens in that fourth period, starting from scandium and ending up in zinc, all right? And you see a similar pattern for the period below, and so on, all right? So that's something that you need to be aware of. When you get to chromium and when you get to cobalt, copper, then basically those are the trends that you'll observe. In the case of the chromium, you find that the half-filled 3D sublevel is more stable than 3D4, and this is also confers some extra stability as well. And then here, the completely filled 3D sublevel is more stable than 3D9, all right? So these exceptions, as I said before, occur further down the periodic table. They aren't always predictable because the energy levels get closer together. So it's difficult to make the predictions when you get to the period 1, 2, 3, 4, 5, like period 6 and so on. It becomes a bit more difficult. This sort of pattern or this exception at these steps is more observable in period 4, and 5. Beyond that, it's not as predictable. Okay, and this is very important when it comes to answering that same question that I left for you guys to do. So again, if you have any problems with those, let me know. All right. Okay. Now at this juncture, it's very important that you understand the difference between what we call valence electrons and core electrons. I think I mentioned valence electrons before, but I'll mention it here. Firstly, let's just say that the valence shell is the highest energy shell, or the outermost occupied principal shell, right? And then the valence shell is what contains the valence electrons. So the electrons that are occupying the valence shells are called valence electrons, all right? Now for the main group elements, the valence electrons, the number of valence electrons would be the same thing as the group numbers, right? So in group 1A, the valence shell, the number of valence shell electrons in those atoms would be 1. In group 2A would be 2, and so on, all right? And then the period number is the same as the principal quantum number n of the electrons in the valence shell. Now, all the other electrons that you can identify within an atom that are not valence shell electrons, these are called core electrons, all right? So let's look at an example. Suppose you're given this. Well, this here is the abbreviated electron configuration for this element, which is arsenic, right? The valence electrons are the electrons occupying the 4th shell, namely the 4s2 electrons and the 4p3 electrons, right? So those are the valence electrons, right? All the other electrons would be the core electron, which include the electrons represented by this right here. So the number of electrons here would be 18 plus the 3d10, the 10 electrons in the 3d subshell. So that's a total of 28 core electrons, right? So it's very important that you understand, for what we're going to do next, you understand the difference between the valence electrons and the core electrons. The valence electrons are the electrons that occupy the highest shell, energy shell, or the outermost shell of the atom, and the other electrons would be the core electrons, all right? This is important because you need to understand this in order to determine the electron configuration of ions. So all along, so far, what we have been interested in is determining the electron configuration of atoms, right? But what about monatomic ions? Well, okay, so when it comes to monatomic ions, we all know how they're formed. The cations are formed as a result of electron loss, and the anions are formed as a result of electron gain, right? So this is something that you have to keep in mind when it comes to determining the electron configuration of ions. So as stated here, to obtain the electron configuration of an anion, what we do is simply add electrons to the valence shell of the neutral non-metallic atom, right? And usually, not always, but usually this results in a full outer shell, all right? And the resulting monatomic ion will end up with, usually again, not always, a noble gas configuration. So for example, in the case of the oxide ion, right, when you add 2 electrons to the oxygen atom, you're going to get a structure which has the same electron configuration as neon. In the case of the bromide ion, when you add an electron to the bromine atom, you're going to end up with a structure with the same electron configuration as krypton, all right? Now, when it comes to dealing with cations, as I said before, electrons are removed. But here you have to be careful in terms of determining the electron configuration of the resulting ion. Basically, when you're removing electrons, you start removing electrons from the shell of the highest energy, or the outermost shell, right? So that's why it says here the first electrons lost are those of the highest principal quantum numbers. And then now, when you get to a situation where you have a choice between removing electrons from, let's say, an s orbital, or s subshell, or p subshell, right? The question is, where do you start removing electrons from? And the answer is you remove electrons from the subshell that is also of a higher energy, right? So in that case, for example, if you have to remove electrons from, if you get to a point where you have to decide where you're going to lose electrons from, an s subshell or p subshell, you start removing electrons from the p subshell, and then you continue until you remove the right number of electrons. And then if you need to, you may need to go to a lower energy subshell, right? So that's why it says here, you start removing electrons from the subshell with the higher L value, right? Remember the L values correspond to the SPD notation, right? L is equal to 0, L is equal to 1. I'm sorry, P, L is equal to 1, B, L is equal to 2, and so on. All right. So just to give you a couple of examples, right? In the case of fluorine, this is the electronic configuration of fluorine, right? To get from the fluorine atom to the fluoride ion, you add an electron, and that electron will be added to the 2p sublevel here, which is not quite filled yet, right? So you're gonna end up with this right here, 1s2, 2s2, 2p6, and that has the same electron configuration as neon, all right? In the case of sulfur, this is the abbreviated electron configuration. To get from sulfur to the sulfide ion, you're gonna add 2 electrons, and those 2 electrons will be added to the 3p sublevels, so that would increase from 4 to 6, and this has the same electron configuration as argon, all right? Now, when it comes to the formation of cations, here are some examples. In the case of strontium, this is the abbreviated electron configuration of strontium. To get from strontium to strontium 2+, you have to remove 2 electrons, and those 2 electrons will be removed from the 5s subshell, right? So when that 5s subshell loses those 2 electrons, that subshell disappears. So therefore, the electron configuration of strontium 2+ would be the same as krypton, right? Now, in the case of titanium, this is the abbreviated electron configuration, and in this particular case, you'd have to start removing electrons from the subshell with the highest N value. So therefore, even though this is of a lower energy than this, it's the quantum number, the N quantum number that determines where you start losing electrons, right? So you're going to start losing electrons from the 4s sublevel, right? And to get from titanium to titanium 4+, you're going to lose those 2 electrons first. I'm sorry. You're going to lose those 2 electrons first, and then you're going to lose these 2 electrons. So therefore, you're going to end up with the electron configuration of argon as the configuration of titanium 4+. Now, in the case of iron, to get from iron to Fe2+, this is the abbreviated version, right, of the electron configuration. So to get from Fe to Fe2+, you're going to lose these 2 electrons first, right? So therefore, that subshell will disappear, and therefore the remaining electron arrangement would be what you see here, right? So this would be the electron configuration of iron 2+, all right? Now, here in this cloud right here is asking the question, what would be the electron configuration of Fe3+, right? Well, that's easy. To get the electron configuration of Fe3+, you're going to remove an electron from here, right? So in the case of Fe3+, the electron configuration,
AR 3D5.
3D5, yeah, AR 3D5, right? So the electron configuration of, I'm trying to write it here, Fe3+ would be AR and then 3D5, right? And that's it. Now, in the case of the next question being asked here, tin 2+, we need the electron configuration of tin. What's your atomic number of tin? Tin is below germanium in group 4. 4A.
It's 50.
50?
Yeah.
Okay. So to get the full electron configuration, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, hold on. So this is, 50. Wow, okay. 3d10. What's the next after 3d?
4P.
4p6. So that's 36, and then what?
5s2.
5s2.
4D something.
4d, okay, so that's 36, 38.
4010.
4010. So that's
48.
48. And then what comes after?
And then 5P2.
5p2. and that will be 50, right?
Yeah.
Okay, so the okay, so if I were to write down the abbreviated version, what's the element that comes before 10? The group 8 element that comes before 10?
Krypton, yeah,
Krypton. And what's the atomic number of krypton?
36.
So that would be everything 36, you said?
Yeah,
36 from 50, that's 14. Okay, yeah. So all of this here will be represented by krypton. So krypton, and then 5s2, 4d10, 5p2, right? So for this is for 10, right? So for 10 4 plus, what would be the electron configuration? Where would you start losing electrons? Remember now, you start losing electrons from the valence shell, or the shell with the highest n values.
it's gonna be KR4D10.
Exactly, 4d10, because
Yeah,
you're going to lose these here and these here. So these will disappear when you lose the first 4 electrons, and therefore you're going to end up with that as the electron configuration of krypton. All right. And that's how you do that. Okay, any questions about this? Any questions? Any questions? Okay, so let's look at this one, right? The electron configuration of CO3 plus in a noble gas abbreviated SPD notation. So what's the atomic number of cobalt?
27.
27, right? So the electron configuration of cobalt will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7, all right? So to write down the abbreviated version, we will replace all of this here with argon, right? And then 4s2, 3d7. Okay, so the question is asking, what would be the electronic configuration of cobalt 3 plus? And that would be what? You have argon and then what?
36.
3d6, exactly. Because you're going to lose the first 2 electrons here, that means this will disappear, and you're going to lose the third electron from here, which is reduced to 6, and that would be the electron configuration of cobalt 3 plus. Okay, very good. Now based on that, we now should be able to do some more questions from the assignments. Namely, okay, so this question is asking part B. Write the complete electron configuration of the following ions and determine which one possess the noble gas configuration. In other words, whether or not it obey the octet or duet rule, having a complete outer shell. So in the case of chlorine, chlorine has an atomic number of 17, right? So that's 17 for chlorine, right? So the electron configuration of chlorine will be 1s2, 2s2, 2p6, 3s2, 3p5, right? That would be the electron configuration of chlorine, the atom. But it's asking for the chloride ion, which means that we need to add 1 electron to the 3p sublevel, so that becomes 6, right? And the question is asking whether or not this obeys the octet rule. In other words, does this have a noble gas configuration? And the answer is yes. And that would be the same as the configuration of the element right next to chlorine, which is argon. So the answer is yes. It has a noble gas configuration. Right? And that's it. Okay, we did cobalt 3 plus already, right? And cobalt 2 plus, that's relatively easy. All you have to do is add an electron to the cobalt 3 plus and you get cobalt 2 plus. So I'm going to skip that one. those two for now. And for chromium 3+, so chromium is one of those weird ones, as I said before. Let me clear this here. The electron configuration of chromium, the atomic number of chromium is what?
24.
24. Now, the electron configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4d1, 3d5, right? Remember, chromium is one of those where the half-fill sublevel, D sublevel is more stable than 3d4, right? Now, for chromium 3+, how would you get that from this here? How would you go from the chromium atom configuration shown here to chromium 3+? Where do you start losing electrons?
4d1.
Okay, so basically you're going to lose.
So it's gonna lose 4d1
Mhm.
and then it's gonna be 3d2. Oh no. 3d3.
Exactly.
And it's install this still the same.
And that's it. All right. Okay, any question about this? Any question? Okay, what about titanium 3+? What's your atomic number of titanium?
No,
TI,
22, yeah.
22, okay. So in the case of titanium, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, you said 22, and 3d2, all right? Okay, so that's titanium. So how do we get from titanium to titanium 3+?
You take away 4s2.
You're going to take away 4s2, yep,
And it's gonna be 3d1.
exactly. So this would be the electron configuration of titanium. So that's basically how you do that, all right? Let me scroll down here to see what's going on. Oh, lithium, oh, that's too easy. Let me clear this here. Lithium is too easy because the atomic number of lithium is 3. Right, so therefore the electron configuration is 1s2, 2s1. So therefore, in this case here, to get to lithium plus, you simply remove that one, which means that the 2s will disappear, and it's going to be 1s2. And remember, each of these, the question is asking for you whether or not the structure will have a noble gas configuration. The others that we did, apart from the first one, will not, right? But this one will. So this one has a noble gas configuration because it has the same noble gas, the same configuration as helium. All right. Okay. Any questions about these? Any questions about any one of these? Any questions? Any questions? Oh, by the way, you guys out there in Zoom, feel free to join in, ask any questions that you may have. Okay, so let me clear this. And let me see if there's anything else we can do before we move on to the next one. Okay, we can do these here. Okay, so let's go back to the PowerPoint. All right. So what we're going to look at are some properties which are directly related to the electron configuration of the atom. Now, one of them is their magnetic properties, right? So let's talk about the different types of magnetic properties that can be displayed by elements. You have what is known as diamagnetism, which is the weak repulsion associated with structures that have paired electrons. You have paramagnetism, which is the attraction associated with structures that have unpaired electrons. And then you have ferromagnetism, which is an exceptionally strong attraction of a magnetic field for iron and a few other substances. Now, the main ones that we'll be concerned with are both diamagnetism and paramagnetism, all right? So remember now, diamagnetism is the repulsion due to pairs of electrons existing in the electronic structure, and paramagnetism is the weak attraction that's associated, well, not so weak actually, which is associated with structures that have unpaired electrons, all right? Now, I have a diagram here which basically shows you the experimental setup for detection of some magnetic properties, right? So basically, you have your sample here in this tube. You have an electromagnetic field that exists right here, or actually not electromagnetic field, a magnetic field that is that can be turned on and off, all right? And then basically, if there's no magnetic field here, then basically the sample here would be in equilibrium with whatever is over here. You can actually determine the weight of your sample directly. And then when you turn on the magnetic field, if the substance is paramagnetic, what's going to happen is that the field is going to pull the substance towards it, and therefore it's going to weigh heavier, right, compared to what it was before the field was turned on, right? So if it weighs heavier when you turn on the field, then you know that your substance is paramagnetic, which means that it has at least 1 ampere, that's all you need, 1 ampere electron in its electronic configuration, all right? So that's how you determine whether or not a substance is paramagnetic, all right? So for example, this question says a sample of chlorine gas is found to be diamagnetic, which means that there are no unpaired electrons present, all right? So the question is asking, can this gaseous sample be composed of individual chlorine atoms? Well, if you were to draw the electron configuration of chlorine, it is basically going to be 1s2, because chlorine has an atomic number of 17, right? So 1s2, 2s2, 2p6, 3s2, 3p5, right? Now remember, within the p sublevel, there are 3 orbitals, right? And if you have 5 electrons distributed among 3 p orbitals, right? What that means is that there's 1 electron which will be unpaired, right? So there is 1 unpaired electron. If there's an unpaired electron, that means that the chlorine atom is paramagnetic. All right? And if it is paramagnetic, that means that, well, in this sample of chlorine gas, which was found to be diamagnetic, it would not consist of individual chlorine atoms. So in chlorine gas, there are no individual chlorine atoms. And we all know this already, because remember, chlorine exists in nature as CO2, right? So therefore we know, based on this experimental finding, that there are no chlorine atoms present in a sample of chlorine, because chlorine atoms have 1 unpaired electron, which would make it paramagnetic, but it's diamagnetic, which means that all the electrons are paired up. So therefore, it doesn't exist as the chlorine atoms. Instead, it exists as chlorine molecules, diatomic molecules. Okay, and that answers that question. Any question about this one? Any question? All right, so let's see what's next. Okay, so that's one property. Let me clear this. The other property that we're going to look at are properties that relates to periodic trends, right? So when we're talking about periodic trends, and this is something that was first observed by the first person who came up with the whole idea of having a periodic table, Mendeleev. He observed certain trends. In those days, I don't know if I told you the story, but in those days, the notion of atomic numbers didn't exist, right? Back then, the only thing that they can define for elements is the atomic mass. And what he did was that he observed that if you order the elements after each other in terms of increasing atomic masses, after so many elements, you see certain properties repeating themselves, right? That's what he observed. And we now know that that observation is due to how the electrons are distributed in the atom, right? So now we're going to get to an understanding as to how that is. How does the arrangement of the electrons in the atom, how does that cause the order of the elements in the periodic table to be what it is that we understand today, all right? So as stated here, certain physical and chemical properties repeat themselves after certain intervals, right? And they vary in a regular fashion according to the increasing atomic number. And we're talking about properties like melting point, boiling point, hardness, density, physical state, chemical reactivity, and so on, right? And we can relate these to their electron configuration. So the first property we're going to look at is the atomic size, right? Now, the atomic size can be determined in different ways for an atom, right? Now, if you're dealing with a diatomic molecule, such as chlorine, hydrogen, and so on, the atomic size can be determined by finding the distance, half the distance between the two nuclei of the diatomic molecule, right? So in this case, I'm not sure which particular element this represents, but whatever element it represents, basically the atomic radius would be 1.33 picometers, because the distance between the two nuclei is 266 picometers, right? So divide that by 2, and that gives you the atomic radius, right? So that is in the case of nonmetals. Now, in the case of metals, it's kind of similar. The metallic radius is half the distance of the nuclei between adjacent atoms in the metal itself. So if you have two atoms next to each other in a metal, the distance between them in terms of the nuclei, you take the half of that, and that will give you the atomic radius. And that is used as a proxy for the atomic size, all right? So that's what we're looking at here when it comes to the trends in the periodic table. Okay, so what is the trend that we observe in terms of the atomic size? Well, if you look at the trend in terms of going from left to right of any period, what you'll find is, going from top to bottom of any group. Let's deal with that first. What you'll find is that the atomic size will increase. Going from top to bottom of any group, the atomic size increases, all right? Now, why does that happen? Well, basically, it relates to the distance between the nucleus and the valence electrons. If you think about going from, let's take group 1, right? In the case of group 1, at the very top of group 1, you have hydrogen. 1 electron, 1 proton, right? So there's a certain distance between those two. And then the next element below is lithium. Now, what happens in the case of lithium? You have a nucleus, right? But you have 2 electrons in the first shell and 1 electron in the third shell, right? So what happens? Basically, you have the electrons in the first shell repelling the electrons in the third shell, in the second shell. And therefore, that places the valence electrons further away from the nucleus, right? We call that the screening effect, okay? So basically, the more intervening shells that you have between the nucleus and the valence electrons, the more further the valence electrons are pushed away from the nucleus, and therefore the distance between the nucleus and the valence electrons will increase, and therefore that results in an increase in the atomic size, all right? So that explains why you see that trend as you go down any group. As you go down any group, the distance between the nucleus and the valence electrons will increase, all right? Now, that's a trend going down the group. What about the trend going across any period? Well, what is observed is that as you go from one element to the next, left to right of any period, the atomic size decreases. As you go from one element to the next, as you go from, let's say, lithium in period 2, ending with neon in the same period, you find that the atomic size decreases, right? Now, why does that happen? Well, let's think about what happens as you go from one element to the next across a period. As you go from, again, using period 2 as an example, you start off with lithium. Lithium has 3 protons, and it has 3 electrons surrounding it, right? And then to go from lithium to beryllium, you add an electron to the nucleus, but you're also adding an electron to the valence shell, right? So the result of that is that the nucleus will have a greater pull on the surrounding electrons, right? You're adding electrons to the same shell while you're adding a proton to the nucleus. So therefore, the atom will become smaller as you go from lithium to beryllium, and that trend continues as you go from beryllium to boron, to carbon, nitrogen, oxygen, and so on, right? So each time, as you go from one element to the next, you're increasing the nuclear charge, you're adding an electron to the same valence shell, right? So therefore, you're decreasing, as a result, the size of the atom because the surrounding electrons will be pulled closer to the nucleus, all right? So that's basically how you can explain that particular trend, going from left to right of any period, all right? Okay, so this graph here basically shows you graphically, of course, the trend that we just described. What you'll find is that when you get to higher periods, like when you get to period 3 and beyond, right? There are some deviations from that trend, but you can clearly see the trend established definitely in periods 2 and 3, whereas you increase, oh, by the way, let me just explain what this graph is. So the y-axis is the atomic radius, the x-axis is the atomic number, right? So this line here represents a trend for period 1 and period 2, I'm sorry, right? Starting with lithium and ending with fluorine, right? And you see clearly there's a decrease in the atomic size as you go from lithium to fluorine, right? And then you see the same trend as you go from sodium to chlorine. You see the same general trend as you go from potassium to bromine with a bit of a kink right here. And that is true also with a bit of an increase here and a kink right here, and then it falls down. And it's even more complicated in the case of the period starting with cesium, right? So basically, that's what you observe. As you go across any period, the general trend is that as the atomic size, as you go from left to right of any period, the atomic size decreases. Okay. So that's basically what atomic size variation occurs going across any period and down the group. Okay, so let's look at this example. It says, with reference only to a periodic table, arrange the following set of elements in order of increasing atomic radius, right? So this question is asking for you to order them in terms of increasing atomic radius, meaning that you're starting from the smallest to the largest, all right? From the smallest to the largest. So based on the positions of the elements indicated in each case, let's start off with A. Which of these would you expect to be the smallest? All right, now, based on what I see here in the periodic table, magnesium, sulfur, and silicon are all in the same period, all right? And what did we say about elements in the same period? As you go from left to right, the atomic size what? Decreases, all right. So of these 3 elements, which would you expect to be the smallest in terms of atomic size?
Silicon.
Sure about that?
Sulfur.
Sulfur, exactly, because sulfur is to the extreme right, followed by,
Silicon.
and then magnesium. Okay, very good. Okay, what about B? Arsenic, nitrogen, and phosphorus. So based on what I see in the periodic table, they all belong to the same group. And what did we say about the groups? As you go down the group, what happens to the atomic size? Increases. Okay, so of these 3, which you'd expect to be the smallest? Nitrogen, followed by phosphorus, followed by arsenic. Okay, very good. All right, so the third series, C, you're given arsenic, antimony, and selenium. Okay, so let me see here. Arsenic is there, antimony is right below arsenic, and selenium is to the right of arsenic. All right, so which would you expect to be the smallest in size? Sure about that? You have arsenic, but you have selenium to the right of arsenic. And remember, we said that as you go across left to right, the size decreases. You see what I'm saying? So therefore, I would put selenium first, then arsenic, and then antimony, because antimony is below arsenic. Going down the group, the atomic size increases. So I'm going to put antimony here. All right, and that's it. Okay, so that's how that will be done. All right. Okay, so let's see. I think there's a question of that type in the assignment. Let me see here. Okay, oh, no, we haven't done ions yet. All right, so we can't do this quite yet, so let me go back to the PowerPoint. Okay, so, let me clear this. And scroll down. Okay, so now we're gonna talk about ions. We talked about atoms and their sizes. We're gonna talk about, the size of ions. Firstly, we're gonna talk about the size of the ion compared to the size of the atom from which they're formed. And also, we're gonna talk about trends with respect to ions in the periodic table, right? So first, we have to define what is known as the ionic radius. And the ionic radius of each ion is the portion of the distance between the nuclei occupied by that ion. So here's an example, magnesium oxide, right? It turns out that the distance between the two nuclei is 205 picometers. And then what they determined was that the portion that is occupied by the magnesium 2+ ion is 65 picometers, and the portion that is occupied by the oxide ion is 140 picometers, right? So that's basically how the ionic size is determined, right? Now, what we're going to look at is comparing the size of an ion to the atom from which it is formed, all right? And first we're going to look at cations. Now we know that cations are formed as a result of an atom losing electrons, right? So basically, when an atom loses an electron, then what will happen is that there will be less propulsion between the remaining electrons, and those electrons will be pulled closer to the nucleus, right? So what you'll find is that cations would be smaller in size compared to the atoms from which they're formed. And that can be seen in this diagram right here. If you compare the sodium atom to the sodium ion, the sodium atom is 186 picometers in terms of its ionic size. The sodium ion is 99 picometers, so almost half. It's almost reduced by half in terms of the ionic size compared to the atom from which they're formed, right? You can also see that in the case of magnesium. The magnesium ionic size is 160 picometers, while that on the magnesium ion is 65 picometers, right? So again, you see there's a drastic reduction in the size of the ion compared to the atom from which they're formed, right? So that is pretty much true. I don't think there's any exception to this particular observation, right? Basically, cations are smaller in size compared to the atoms from which they're formed, all right? And the reason is there's less electron-electron repulsion when you remove an electron or two, right? The nucleus will basically have a greater hold and pull on the remaining electrons, and therefore the ion will be of a smaller size compared to the atom from which they're formed. All right, so that's as far as cations are concerned. Now, when it comes to anions, the opposite is true, right? Because in the case of anions, to get from an atom to an anion, what do? You add electrons to it. That increases repulsion, right? And therefore the ionic size will be larger compared to the atom from which they're formed, right? Now, there's a term here that I'm going to introduce right now called isoelectronic, right? Basically, that term is applied to structures that have the same number of electrons. So if you have two ions that have the same number of electrons, they're said to be isoelectronic. And what you're going to find is that if you have two species that are isoelectronic, the one with the greater nuclear charge will be smaller, right? Because think about it. If you have two species that have the same number of electrons, right? The one that has a greater nuclear charge will have a greater pull on the surrounding electrons and therefore will be smaller. So do I have an example here? No, but let's say, for example, you compare, if you compare, what is happening here? If you compare, let's say, magnesium 2+ to sodium plus, all right? Now, in the case of magnesium 2+, what am I going to do this? Magnesium 2+ has 12 protons and 10 electrons, right? Sodium has 11 protons and the same number of electrons, 10 electrons. So therefore, these are isoelectronic because they have the same number of electrons. The difference, of course, would be the number of protons. Magnesium has 12 protons, while sodium has 11 protons. So between these two, the magnesium ion will be smaller in size compared to the sodium ion. right? The magnesium ion will have a greater pull on the surrounding electrons compared to the sodium ions, and therefore the magnesium ion will be smaller as a result. All right. So we can take that into account when you're comparing sizes of isoelectronic structures, right? The one with a greater nuclear charge is the one that would be smaller in size because of the greater pull that the nucleus will have on the surrounding electrons. Okay, going back to anions. So what this is showing you here is comparing the radius of the chlorine atom compared to the chloride atom. And again, you see that because the electron added to the chlorine atom will increase repulsion in the chloride ion will have a larger size compared to the chlorine atom. Okay, so much for that. Let me clear this and scroll down. Okay, so this diagram here basically shows you, it gives the general trends of what we were discussing, how atomic sizes and ionic sizes vary across a period and down a group and all that good stuff, right? So let me just highlight a few trends, all right? So the purple spheres represent atoms, the orange spheres represent ions, right? In fact, the orange spheres, to be more specific, represent cations. What color is this? Blue spheres represents anions, all right? So the first thing I want to highlight, as I said before, is that the cations are smaller in size compared to the atoms from which they're formed. And you can see that over here, for all these here, for example, lithium is 59 picometers, that's a lithium ion, compared to the lithium atom, which is 152 picometers. Just to highlight another arbitrary example, strontium, the atomic size is 215, the ionic size is 113. So again, you see that the ion are smaller in size compared to the cations, I should say, are smaller in size compared to the atoms from which they're formed. Okay, over on this side, if you compare the anions to the atoms from which they're formed, you see that the anions are larger. For example, in the case of the nitride ion, its size is 171 picometers, whereas the atomic size is 75 picometers. Or if I were to choose bromine, the bromide ion is 196 picometers, and bromine is 114 picometers, all right? Okay, you can see the trends in terms of the atomic size increasing going from left to right of any period. So if you start with lithium and end with fluorine, you see that it starts with 152 in the case of lithium, decreases to 111, and it continues to decrease until you get to fluorine, which is 71. And then, of course, trends down the group, the atomic size increases going down the group. You see that there are no exceptions to this. Basically, as you go down the group, the atomic size increases. All right, so those are just some of the trends that you'll observe. Also, you can see, for example, that let's say we're dealing with some transition metal ions of different types for the same element. If you look at, for example, chromium 3+ and chromium 2+, right? The size of the chromium 3+ is 64 picometers. The size of the chromium 2+ is 84 picometers, right? One can clearly see that the chromium 3+ is smaller compared to the chromium 2+, right? That makes sense because the chromium 3+ has one less electron compared to the chromium 2+. So therefore, the nucleus will have a greater pull on the surrounding electrons in the case of chromium 3+, and therefore its size will be smaller compared to the chromium 2+. Okay, so let's look at this example. So this question says, referring only to the periodic table, right? And not to the figure that I just showed you, right? So just using the periodic table. The question is asking for you to arrange the following species in order of the expected order of increasing radius. Now, the first thing, whenever I get a problem like this, the first thing I would try to do is identify the isoelectronic species, because the isoelectronic species, as we said before, have the same number of electrons but different number of protons. Once you determine that, it's easy to establish their order, right? So what I'm going to do is construct a little table here. Here I'm going to put electrons, and here I'm going to put protons, right? Now in the case of calcium, calcium has an atomic number of 20, so therefore 20 minus 2 will give you 18 electrons, right? Iron will have, oh, by the way, number of protons will be 20 in the case of calcium. In the case of iron, the atomic number of iron is what? 26. So this would be 26. 26 minus 3 gives you what? 23. Okay. And then potassium. Potassium has 19 protons, minus 1, 18 electrons. Sulfide has 16 protons, plus 2, 18 electrons. And then selenium, what's the atomic number of selenium? 34 protons and 36 electrons. All right. Okay. Now, the calcium, the potassium, and the sulfide are isoelectronic, right? So basically, I can tell that the calcium would be the smallest because it has the highest nuclear charge, followed by potassium, followed by sulfide. All right. I can also see that because selenide is below sulfide in the periodic table, I can place that right here. Right? The selenide will have a greater size, ionic size compared to the sulfide. So that means that we have to talk about Fe3 plus, and basically the Fe3 plus, let me see, Fe3 plus is to the, well, Fe is to the right of calcium, which means that its atomic size will be smaller, and therefore the ionic size will even be smaller. So therefore, I'm going to put Fe3 plus right here. And that would be the order. All right? So that's how you can establish the order of the ions based on their electronic structure. So as I said before, the first thing I would do is I would look for the isoelectronic species, those species that contain the same number of electrons. Once you establish those, then you can order them because basically the one that's smallest is the one of those species, the one that has the highest nuclear charge. And then you try to figure out the others based on their relative positions in the periodic table. All right? Okay. So now I think, what time is it by the way? Okay. So now I think we can look at this question, part C. It says, you would arrange them in each case in order of increasing atomic size or increasing sizes, right? So you're given Fe2 plus Fe and Fe3 plus. Now this should be easy. What would be the order? Which would be the smallest? The Fe3 plus would be the smallest. So Fe3 plus followed by Fe2 plus followed by Fe. Okay, very good. Okay, what about these? S2 minus, argon, and Se2 minus. So again, what I would do is try to find out the isoelectronic species so let me do protons and electrons, right? So sulfur would be 16 protons and 18 electrons. Argon would be 18 electrons and 18 protons. And then the selenide would be 30, what was it again? 34 protons and 36 electrons, right? Now, between these two, the sulfur and argon, the argon will be smaller, right? Because they have the same number of electrons, but argon has a higher nuclear charge, right? And the question now becomes, where does Se2 minus fall? And that would be here, because Se2 minus is below S2 minus in periodic table. As you go down any group, the size increases. All right, so that would be the answer for B. All right. Okay. Any questions so far? Any questions? Any questions? Okay. What about C? In the case of C, they gave you aluminum, chlorine, sulfide, and potassium. All right, so let's deal with the electrons first. Aluminum has 13 electrons. The chloride has 17 plus 1, 18 electrons. Sulfide has 18 electrons. And potassium has 18 electrons, 19 minus 1. In the case of the protons, aluminum would be 13, chloride would be 17, sulfide would be 16, potassium would be 19. So these are isoelectronic. They have the same number of electrons, right? So we can establish that potassium would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to chloride, which would be smaller compared to chloride, which would be smaller compared to potassium, which would be smaller compared to sulfide, which would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to chloride, which would be smaller compared to potassium, which would be smaller compared to sulfide, which would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to potassium, which would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to potassium, which would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to potassium, which would be smaller compared to chloride, which would be smaller compared to sulfide, which would be smaller compared to potassium, which would be smaller compared to chloride, which would be smaller compared to compared to sulfide. All right, so the question now becomes, where does aluminum fall? And in the case of aluminum, because aluminum is in period 3, while the others, let's see, aluminum is in period 3. Well, aluminum is to the left of sulfide and it's above the period which contains potassium. It's right, so aluminum 3 plus, no, hold on, aluminum, what am I saying?
Is in the same group as chloride.
It's in the same period as chloride. But that's an interesting one. Aluminum, if it wasn't for the negative charge, aluminum would definitely be larger. But because chlorine gains an electron, I would put aluminum here. Because for one, I would expect it to be smaller in size compared to the potassium, and definitely smaller in size compared to the chloride and sulfide. So I will put aluminum here. All right, at the beginning, smallest. All right, any question about this? Any questions? Any questions? Okay, let me clear this here. Let's go down. And then now let's look at this one, sulfide, chloride, potassium, and calcium. So in this case here, again, I will look at the number of electrons in each of these. Sulfide will be 18, chloride will be 18, potassium will be 18, and calcium will be 18. So this is very easy because all we have to do is look at the difference in your nuclear charges. Sulfur will be 16, chloride will be 17, potassium is 19, and calcium is 20, right? So the order would be, calcium would be the smallest, followed by potassium, followed by chloride, followed by sulfide. And that would be the order. All right. Any questions about this? Any questions? Any questions? All right. Let me do this. Scroll down. Okay, so now we have to go back to the PowerPoint because now we have to discuss trends, another trend, and that trend has to do with a particular property known as ionization energy. Okay, so what do we mean by this term ionization energy? By definition, the ionization energy is the energy required to remove an electron from a gaseous state, ground state atom. All right. So in other words, we're talking about the energy required for this to happen. You start off with your atom, you remove an electron, you end up with the ion being formed. The energy required for that is called the ionization energy. And this is usually expressed as kilojoules per mole of atoms, right? Now, of course, you have atoms that have more than one electron, right? So therefore you can remove one electron, right? And then move another electron and so on. So each time you remove an electron, energy will be required, right? So that's why we have this term called first ionization energy, second ionization energy, and so on, right? The first ionization energy is the energy required to remove the first electron. The second ionization energy is the energy required to remove the second electron, and so on and so forth, right? And what you'll find is that as you remove each electron, it becomes more difficult to remove it, and therefore more energy is required. So the energy required to remove the first electron will be of a certain value. The energy required to remove the second electron will be of a greater value, and so on and so forth. And the reason has to do with the fact that each time you remove an electron, the resulting structure will have a greater positive charge, and there to remove the next electron, you're now removing an electron from a structure which has a greater positive charge that requires more energy, right? So that's why we observe that trend, okay? The first ionization energy will be lower than that of the second, which will be lower than that of the third, and so on and so forth, right? Now, here's a question being asked, right? It says here that there's a large jump or a large increase in the ionization energy after the valence electrons are removed, right? So basically, what they're saying is, okay, a certain amount of energy is required to remove the electrons from the valence shell. And then once those electrons are removed, then a greater increase in energy is required to remove electrons from the second or the next valence electron. I'm sorry, next valence shell. Why is that so? Why do you think that is so? Why there's a large increase in the amount of energy required to remove the electron when you get to the next shell after the valence shell?
Because the next shell is closer to the nucleus.
There you go. Exactly. The next shell will be more closer to the nucleus, and therefore the nucleus will have a greater hold on those electrons. So therefore, more energy, a significantly more energy will be required to remove those electrons each time you get into the next valence shell, right? Okay. Okay, so that's as far as going down a group. No, actually, we didn't get into that yet. Okay, so let's focus on the first ionization energy, the energy required to remove one electron, right? So what is being stated here is that as you go down any group, right, the energy required to remove that first valence electron will decrease, right? And again, it's kind of related to what you just said, right? Because as you go down any group, the distance between the valence electron and the nucleus increases, right? So therefore, the nucleus will have a less hold on the valence electron, and therefore it's easier to remove the valence electron, right? There are some exceptions. Well, no, actually, there are no exceptions that I can think of in this particular trend, right? So going down any group, the first ionization energy decreases. Now, going across any period, let's think about what happens in this case. Now, this is kind of related to something we mentioned before. As we go across any period, right, the distance between the nucleus and the valence electron will decrease. So as a result of that, the ionization energy will generally increase, right? So going from left to right of any period, the energy required to remove the valence electron would generally decrease because of the increasing, or I should say the decreasing distance between the nucleus and the valence electron, all right? Now, there are some exceptions to this, right? And these are actually slight exceptions, and they're actually an explanation for that. And I think the next slide deals with, hold on, let me see here. Okay, so this slide here is showing you the first and second ionization energy for the elements in group 1A and 2A, all right? Now, we're going to get to the exceptions that I just mentioned later on, but for now, I want you to pay attention to, okay, let's look at a comparison between lithium and beryllium, right? Now, if you look at, let me see here. Okay, if you look at the first ionization energy for lithium and compare it to the second ionization energy for the same atom, there's a significant difference, right? 520 compared to 7,298, right? We understand the reason why that happens, because in the case of lithium, you have one electron in the first shell. When that is removed, that's the amount of energy that's required. To remove the next electron, you have to go to the next shell, which is even closer to the nucleus. So therefore, more energy is required for that. And that's the reason why this much energy is required, right? So we understand that in the case of lithium. And you see that trend not only for lithium, you see that for sodium, you see that for potassium, all the elements in group 1A, right? Now, in the case of the elements in group 2A, starting with beryllium, the difference here is not as large, right? To remove the first electron, the energy required is 900. To remove the next electron, the energy required is almost double, 1,757, right? In that case, we can understand the reason why. The reason why is because in beryllium, the two electrons to be removed are in the same shell, right? So you remove one electron from that shell, you remove the second electron from that same shell. So therefore, the amount of energy required collectively is not as large as in the case of lithium, where you're removing one electron from the first shell and then the second electron from the next shell, right? So we understand that trend. And we see a similar trend for magnesium, for calcium, all the elements in group 2A, right? So therefore, we can understand those differences based on our understanding of the electron configuration. And this basically verifies what we just said earlier. basically, once you get from one shell to the other, the amount of energy required to remove the electron from the subsequent shell is significantly larger compared to the electrons removed from the previous shell. Okay, all right, so that's that. I don't think there's anything else I should say. About that. Okay, so this is where the exception that I mentioned earlier comes into play, right? So what this is showing you is how the electron config, how the ionization energy varies as you go from left to right of any period. So the top part here is referring to period 2, starting with lithium and ending in neon, and then this is starting with period 3, sodium to argon. All right. So if you look at the trend going from lithium to boron to beryllium, there's an increase, 520 to 900, right? And then there's a slight drop going from beryllium to boron from 900 to 801, all right? So this begs the question, why is it that there's a drop in the ionization energy going from beryllium to boron? So in order for us to understand the reason why that happens, we have to look at the electronic configuration of beryllium, which is the electronic configuration of helium, and then 2s2, and boron, which is the electronic configuration of helium, and then 2s2, 2p1. All right. Now, in the case of beryllium, the first ionization energy corresponds to the losing of an electron from an s subshell. In the case of boron, that would correspond to the losing of an electron from a 2p subshell, right? So this explains why there's a slight drop here, because the 2p sublevel is of a higher energy compared to the 2s sublevel, right? So therefore, what this indicates is that the electron in the 2p sublevel is slightly further away from the nucleus compared to the electron in the 2s sublevel in the case of beryllium. So therefore, this electron here is easier to remove. And therefore, the energy would fall going from beryllium to boron in terms of the first ionization energy, right? So that's how we can explain that particular observation going from beryllium to boron. The ionization energy drops slightly, and that's because the electron here in the 2p sublevel is slightly further away from the nucleus compared to the electrons in the 2s sublevel. And therefore, that's the reason why it's easier to remove, all right? Okay, another thing that we observe, another exception that we observe is that, well, starting from boron, the energy increases to carbon, and then it increases to nitrogen, and then there's another decrease, all right? Right here, the energy, the first ionization energy decreases again slightly from nitrogen to oxygen. Now, why is that so? Again, we have to go to the electron configuration. So the electron configuration of okay. The Wi-Fi just dropped me. So I have to reestablish. Okay, I have to reestablish contact here. Oh, I think it's reestablished. You guys out there, can you hear me? You guys out there in Zoom, can you hear me?
Yeah, we can hear you.
Okay. Oh, okay, good. All right. Yeah, the Wi-Fi signal just dropped a while ago, so. Thank you, Mr. Lanza. Okay, so let me go back to share my screen. Okay, so I was saying that the first ionization energy dropped going from nitrogen to oxygen. So I was about to write down the electron configuration of both nitrogen and oxygen. So for nitrogen, I'm going to do it over here. Nitrogen has an electron configuration of 1s2, 2s2, and what I'm going to do here for the p orbitals, I'm going to use the box diagram, right? There are 3 electrons occupying the 2p sublevel, and each sublevel each orbital will have a single electron. So that would be the electron configuration of nitrogen. In the case of oxygen, that would be 1s2, 2s2, but in this case here, you're going to have 3 p sublevels where 2 of them, 2 electrons will crowd into one of the p orbitals, right? So basically, what's going to happen is that you're going to have 2 electrons sharing the same p orbital. Now we know that electrons don't like each other, they will repel each other, right? So therefore, that explains why the oxygen here will have a slightly lower first ionization energy, because the repulsion between these 2 electrons will make this electron easier to remove. All right? So therefore, in the case of oxygen, its first ionization energy would be lower compared to the first ionization energy of nitrogen. And that explains why there's a drop in the ionization energy as you go from nitrogen to oxygen. All right? So that's what happens in that case. So those are just 2 unusual deviations from the general trend. The general trend is that there would be an increase in the first ionization energy, but there's a slight decrease going from beryllium to boron and also going from nitrogen to oxygen. And I just explained the reason why. All right. Okay, so let me right, so what I just stated is in this green box right here. Repulsion of the paired electrons makes that electron easier to remove. All right. Okay. Any questions? Any questions? Any questions? Okay. So this graph, let me just give this here. Basically shows you the trend that I observed that we discussed. Excuse me. So the first ionization energy is plotted on the y-axis, the atomic number is plotted on the x-axis. And what I just discussed for the second period is shown by this part here, where you start with lithium here and end with neon right here. So basically, the first ionization increases until you get to boron. It drops slightly for beryllium, and then it increases again until you get to nitrogen, and then it drops slightly for oxygen, and then it increases up to neon, right? So that's basically what we were discussing earlier. And we see a similar trend for the next period. This is sodium. The period starting with sodium, period 3, and ends with argon. Again, you see an increase, then a drop from magnesium to aluminum, and then you see an increase again, and then you see a slight drop from phosphorus to sulfur, and then it increases again to argon. So you see those 2 trends for periods 2 and 3. Beyond that, it becomes confusing, right? When you go to period 4, 5, 6, it becomes more complicated. All right. Okay. Let's see here. So this is what I just described. And then it says the change becomes small at higher energy levels, so it becomes more complicated. All right. So let's look at these questions, these examples. Question says, arrange each set of elements in the expected order of increasing first ionization energy. So we're starting from the lowest to the highest, right? So here you're given magnesium, sulfur, and silicon. So again, we have to refer to the periodic table. So magnesium is over there, silicon is in the middle of that period, and sulfur is at the end. Okay, so which one of these would you expect to have the lowest first ionization energy? Between these 3, magnesium, sulfur, and silicon, they're all in the same period. And what did we say about the period in terms of the first ionization energy? As you go from left to right, what happens? It increases, right? So which of these 3 would you expect to have the lowest? Magnesium would be the lowest, followed by silicon and then sulfur. Very good. Okay, for B, arsenic, nitrogen, and phosphorus. Now, in this case, they're in the same group. What did we say about the group trend going down for the first ionization energy? It would decrease. All right. So which would have the lowest between the arsenic, the nitrogen, and the phosphorus?
Arsenic.
Arsenic, followed by, exactly. Okay, and then we get to see arsenic, germanium, and phosphorus. Okay, let's see. So arsenic is there, germanium is to the left of it, and phosphorus is above. So of these three, which would you expect to have the lowest first ionization energy between arsenic, germanium, and phosphorus? Okay, I would say germanium because germanium is to the left of arsenic. Followed by arsenic, and then phosphorus. Exactly. Okay. So that's how that will be done. All right. So now I think we can do. By the way, welcome. Okay. I think we can do some more problems from the assignment. Let's see here. Let me clear this here. Okay, so this question, well, the first question is define ionization energy. I already answered that, right? The ionization energy is the energy required to remove an electron from a gaseous atom in its ground state, all right? So the next question is what trend in the ionization energy as you see as you go down a group? We know the answer to that. It increases as you go down a group, right? And the next question is what causes this trend? Why is it that as you go down the group, the ionization energy decreases? And the answer is that as you go down the group, the valence electrons are pushed further away from the nucleus due to the screening effect of the inner core electrons, and therefore the force between the attractive force between the nucleus and the valence electrons will decrease, which means that the electrons in the valence shell would be more easier to remove, and that's why the ionization energy decreases going down the group. The next question is asking, what trend in ionization energy do you see as you go across a period? And the answer is, of course, it decreases. And we know the reason why. As you go from one element to the next, you're adding a proton to the nucleus, you're adding an electron to the same shell. The consequence of that is that the electrons will be pulled closer to the nucleus and become more difficult to remove. And therefore, that's the reason why the first ionization energy decreases. Generally, remember the exceptions we talked about, right? But generally, the first ionization energy decreases as you go from left to right of any period. So that brings us down to question number 6. Circle the atom in each pair that has the greater first ionization energy. Greater first ionization energy. So between lithium and beryllium, which of those two would you expect to have the greater first ionization energy?
Beryllium.
I'm sorry?
Yeah.
Which would you expect to have the greater first ionization energy? They're in the same period. What do we say about going across a period? For the ionization energy. The ionization energy would increase. Exactly. So which of those two you would expect to have the greater? Beryllium. Exactly. Okay, very good. Sodium and potassium. Now in this case, sodium is above potassium in the same group. Right? And what did we say about going down a group? It decreases, right? So which of these would you expect to have the greater first ionization energy? Sodium, exactly. What about chlorine and silicon? Okay, where are they? Chlorine is to the right of silicon. So which one of those two would you expect to have the greater first ionization energy? Chlorine, okay. What about calcium and barium? Which of these two, where's calcium? Calcium is there and barium is below calcium in the same group. So barium would have the lower first ionization energy. The question is asking for the greater, right? So the answer would be calcium, right? Remember the trend is increasing going down the group, all right? And then we have, anyway. Then we have phosphorus and argon. Okay, so phosphorus and argon are actually in the same period. So which would you expect to have the greater first ionization energy? Argon, exactly, so. Argon. And then lithium and potassium. Which would you expect to have the greater, between those two, the greater first ionization energy? Lithium, okay, very good. All right, now, in the case of number 7, it's asking for you to rank them from lowest to highest first ionization energy. So you're going to start with the lowest to the highest. So the first one is magnesium, silicon, sulfur. So magnesium, silicon, and sulfur are the same period, right? So which one would have the lowest? Magnesium, followed by? So it's actually the same order as they gave us. All right. Okay, very good. What about B? Magnesium, calcium, and barium. Which would be, of these three, which would be the lowest?
Barium, calcium, magnesium.
Barium, calcium, and magnesium. Okay. What about F? Fluorine, chlorine, and bromine. Which would be, what's the order? In terms of first ionization energy.
Bromine.
Bromine, chlorine, and fluorine. Okay, very good. All right, let me see, is there any more down here? And then silicon, phosphorus, and helium. Let me just clear this here. Silicon, phosphorus, and helium. Okay, so silicon, where's silicon? Silicon is there. Phosphorus is
Next to it.
next to it, and helium is up to the top, right corner. Okay, so these three, which would you expect to, what's the question again? You're going from lowest to highest, right? Yeah. Okay. Lowest to highest, okay. So which of these three would you expect to have the lowest first ionization energy? Let me see here, so silicon, phosphorus, okay. So yeah, which you expect to have the lowest first ionization energy?
Silicon,
Silicon. Followed by
phosphorus,
phosphorus, followed by
helium.
helium. Okay, very good. All right, so that's basically how that will be done. And I didn't realize it, but this is actually the end of this assignment. Okay. Let me, whoops, not there. Let me open up a Dropbox for this assignment. And this is assignment number 8. And I'm going to let this be due tomorrow. So okay, so the 10th, and then okay. Okay, so it's due tomorrow at midnight. All right. So what else do we need to discuss as far as the PowerPoint is concerned? Okay, let's talk about electron affinity, which is another property of atoms. It is the energy change that occurs when an electron is added to a gaseous atom. So it's kind of like the opposite of ionization energy, right? So in other words, you start off with a gaseous atom, it gains an electron to form the corresponding anion. The energy change for that is called the electron affinity. The electron affinity will become important in the next chapter when we're dealing with what is called the Born-Haber cycle. A negative value, of course, means that the process is exothermic, which is the case for nonmetals, right? They have a larger magnitude for the value of the electron affinity compared to metals. And that's because nonmetals prefer to form and ions. All right, so basically what you find is that the electron affinity becomes more negative as you go from left to right of any period, or going from bottom to top of any group. All right, and this is just a table with some selected electron affinity values, right? And the trends, as I described before, are generally true, but again, there are some exceptions, right? But as I said before, electron affinities will become important later on. So we won't deal with it too much in this chapter, all right? Okay, just some general information concerning the elements. There are some other categories that we can put elements in. You can put them in the categories of metals, non-metals, and metalloids, right? So metals, they have, relatively speaking, a small number of electrons in their outer shell, and they tend to lose these electrons to form ions. For example, aluminum will lose the 3 valence electrons to form the aluminum ion, right? All S block elements, with the exception of hydrogen and helium, all D block elements and some P block elements are metals, all right? So this brings us down to what we call the metallic character, which is related to terms that we met before, atomic radius and ionization energy, right? And we can observe these characters variation as you go across a period and down the group, which is demonstrated in this diagram right here. So basically what you'll find is that as you go down any group, the metallic character increases. As you go from right to left of any period, the metallic character increases, right? And that's related to the first ionization energy and the atomic radius of the atoms, all right? Non-metals are basically the chemical opposite of metals in that they tend to gain electrons. They tend to have a larger number of electrons in their valence shells, and they tend to gain electrons in order to complete their octet, right? And therefore, as a result, they form ions, right? All nonmetals are p-block elements with the exception of hydrogen and helium. And the trend in terms of non-metallic character is the opposite of what we observe for metallic character. So as you can see here, non-metallic character increases going down, going up a group and left to right of a period. Or I should say right to left of a period, right? And then we have a minority group of elements known as metalloids. There are 7 of them, if I remember correctly. And you'll find them on exactly on one side or the other of the line, which is the line of demarcation between between metals and non-metals, all right? And these are the metalloids, all right? And they're called metalloids because they have some characteristics in common with metals and other characteristics in common with non-metals, all right? And this is just a summary of all the different trends that we just discussed, right? So you should be able to predict these trends, like if you're given questions of the type that we just discussed, if you're given 3 arbitrary elements, you should be able to tell, okay, what's the order of first ionization energy or metallic character or whatever, simply based on their relative positions in the periodic table. So for example, you could be given this question, indicate which element is more metallic in each case. So what would be the answer for A? Between barium and calcium, which would you expect to be more metallic? Barium, exactly. What about between tin and antimony? Which would you expect to be more metallic? Okay, tin and antimony are in the same period, but tin is to the left. So, exactly. And then you have germanium and sulfur. Which of those two would you expect to be more metallic? Germanium, exactly. All right. So yeah, questions like that you should be able to do based on understanding and knowing the trends. Okay. Just some general information here concerning noble gases. Noble gases, they occupy the column to the extreme right of the periodic table, which would be group 8A. They're called noble gases because they're very unreactive. In fact, for argon and elements below argon, in order for them to react with anything, you have to employ some real unusual special conditions. And last I checked, nobody has been able to make compounds with helium and neon, right? Nobody has been able to successfully react those 2 elements with anything else, all right? And that's pretty much all I'm going to say about group 8 elements. Nothing too interesting about them in terms of reactivity. This section deals with flame colors. We can actually use flame colors to help to identify the presence of certain metallic ions, right? Basically what you'd have to do is take a piece of nichrome wire, which is basically an alloy of nickel and chromium, and you dip it in your solution containing the ion, and then you put it in a flame, and you get these different colors which will indicate the type of ion that is present, right? And this is basically what you'll see for potassium, sodium, and so on, right? And the reason why this works is because the electrons in these metal ions will be excited as a result of the energy of the flame. They will move up to higher energy states and then fall back to lower energy states, and that will result in the emission of a particular color of light, right? So different ions will basically give different colors, all right? And then some general information about the halogens. They are generally good oxidizing agents, and what you find is that the oxidizing power increases as you go up the group. So therefore, fluorine will oxidize a chloride ion, chlorine will oxidize a bromide ion, and so on and so forth. So for example, what is shown here in this picture is where chlorine is bubbled into a solution which contains iodide ions. So because chlorine is more electronegative than iodine, the chlorine will oxidize the iodide ion. In other words, this is the reaction that will take place. You're going to have Cl2 plus I minus, and you're going to need two of these to form I2 plus Cl minus. And what's going to happen is the formation of iodine, which forms this purple color in the solution. All right. In fact, if I'm not mistaken, this is, they have a solvent, organic solvent here, which actually pulls the iodine into the solvent. I think it's carbon tetrachloride, I could be wrong. But you're going to end up with this purple color here as a result of the iodine going into that solution. Okay, yes, carbon tetrachloride is indeed the solvent. Okay, the metals on the other hand, they tend to be good reducing agents because they tend to lose electrons, right? And that's because, of course, the electrons are further away from the nucleus, they're loosely held, and therefore they will give up those electrons in their reaction. So for example, if you take a small piece, and I think this is potassium right here, and you add it to water, you get a very exothermic reaction where the potassium gives up its electrons to the water to form a basic solution. In the case of calcium, which is what is shown here, you need to heat it in order for the reaction to take place. So that's less reactive, all right? So, oh, that's calcium here in this case. This here is magnesium, okay. And then we have the difference between acidic, basic, and amphoteric oxides. Acidic oxides are oxides which produces an acid in water, and this is basically generally true for non-metallic oxides. Basic oxides are oxides which produces bases when added to water, and that is true for metallic oxides. And then you have a third category of oxides known as amphoteric oxides that can react either as an acid or a base. And metalloids, they tend to form amphoteric oxides as well as other heavier metals such as lead, tin, and so on. And that's it for this chapter, all right? So make sure you turn in that assignment, and we're going to start with chapter 9 tomorrow.
So is that chapter 8 on the next test?
So you were testing up to chapter 5, right? 6, yeah, chapter 8 will definitely be on the next test, yeah. Okay, folks. Let me